Next heading you write down. Factors, we are done. Factors affecting the rate of the reaction. Now the other part in this chapter we'll see. Mechanism of reaction. We know mechanism is what? It is the step-by-step description of the reaction. Like what all steps are involved, which is the slowest step, rate determining step, and what all intermediate forms, stability of intermediates and all. All these description will get from the mechanism of reaction. Correct? So this information you have already. I'm directly moving into some examples and the rate expression that we write in all these examples. Okay. You see here, if you have a reaction, say H2 plus I2 gives HI. This reaction is a complex reaction. H2 plus I2 converts into 2HI. Overall reaction is this, but this is a complex reaction. So complex reaction, we know there are different various number of steps involved into this. It is not single step reaction. So what all steps involved into this? What happens here? In the first step, the I2 iodine decomposes into the atomic form, and this is a fast step reaction we have. And then the hydrogen H2 take this atomic iodine and converts into H2I. These are intermediates actually. H2I, this is also fast. And then this H2I again combines with the another iodine atom and converts into 2HI. Slow. So this is RDS, the last one. Okay. The molecule, the reactant molecule is H2 and I2. H2 and I2 reacts by these three steps and converts into HI. So overall reaction, if I write down, will add all these three. And overall reaction I'll write down. So overall reaction would be, when you add these three, this H2I will get cancelled. I2I will get cancelled. So reaction is H2 plus I2 gives 2HI. Okay. Now this reaction involves three different steps. Now the graphical representation of these three steps is the mechanism of the reaction, right? So if I write down the rate expression for this reaction, that would be rate constant K into H2 into I2. Okay. Now, if I try to express this three reaction in the form of graph, okay, how do we express it? Did you copy this?
Yes.
Okay. Now we have three steps. So I'll draw. So I'll draw the coordinate axis. For the first two steps, we are not sure in terms of one term. Third steps, we are very sure. Okay. One second. Yeah. So the x-axis we have is the reaction progress or the progress of reaction. And y-axis is the energy, potential energy or energy we can say. Okay. So suppose the energy of the reactant is suppose here at this point we have the reactant, right? It is the energy of the reactant. H2 plus I2. So this H2 and I2 collides with each other. The energy increases, goes to a maxima, then it decreases, right? And then again, it forms an intermediate here. What is that intermediate? We'll write down later. And then again, the energy increases. Is this? And then again, the energy increases. And this converts into the product here. Okay. The product here is 2HI. Here is 2HI. This is the reaction we have. Now, if you try to understand this, how the reaction proceeds, any reaction when it happens, the reactant molecule collides, its energy increases and increases and increases, goes to a maxima value. At this point, we'll get the activated complex. Okay, this activated complex either converts into an intermediate or product or converts back into the reactant molecule depending upon the condition. That condition we'll discuss in the next topic. But here you just assume these two collides, energy increases, forms an activated complex, and then it converts into the reactant. Sorry, what we say? Converts into the intermediate, which is 2I over here. The intermediate here is 2I. I'll just do some correction here. We have taken H2I2, but the reaction is taking place, means I2 is converting into 2I, the first intermediate we have here. One general graph also I'll draw. Then this I reacts with H2 and forms a second intermediate, which is H2I. This H2I again reacts with I and converts into this. Okay. Now you see one thing here. This energy gap from here to here is the activation energy for first step, EA. Energy of reactant to the activated complex. Activation energy of first step. This is the activation energy of second step. This is the activation energy of second step. So EA1 for the first step, EA2 for the second step, and this is the activation energy for the third step, EA3. This is EA3, third step. So first of all, what points you can understand here. If I ask you, suppose this graph is given, right? Obviously, if you relate this graph and the reaction that we have written, there are 3 steps in the reaction, correct? I want you to look at the reaction H2 plus I2 gives 2HI. 3 steps involved. So 3 steps were there in the reaction, and the number of steps that we had, equal number of peaks we get here in the graph, number of peaks. Right? Number of peaks, first thing. Number of intermediate that forms, number of intermediate is 2, and that will be equals to the number of peak minus 1 plus, or we can also say the number of steps minus 1. N number of steps we have, so n minus 1 intermediate will get. Okay, n number of peaks, N-1 intermediate you'll get. Okay. Here. One more relation you see, which is the most important one here. If you look at this relation of activation energy, K is equals to A e to the power minus EA by RT. So obviously the reaction is taking place at some temperature. Temperature is not a concern over here. But if I ask you, as temperature increases, what happens with K? K also increases. Seen that with temperature increase, rate constant increases. As EA increases, as EA decreases, I'll write down. Activation energy decreases, so rate constant K, what? Increases or decreases?
Increases.
Increase. Correct. So what we can say that for a given complex reaction, we have n number of steps. All these steps will have its own activation energy. As the activation energy increases, the rate of the reaction becomes more, the reaction becomes faster. Correct. So if I ask you here, which step is the slowest step? What is your answer?
Third
The
step.
one which has the highest activation energy. Are you getting my point?
Yes, sir.
Right. So the one which has the highest activation energy is the
Slowest step.
slowest step. Correct. So first step you see what I did here. Yeah. 1 second. Just play. That's nice. As activation energy decreases, EA decreases, so K decreases, no? Yeah, right only. So if EA is more,
So it's correct, right?
no, we should have the third step is the fastest step, no? Third should be slowest. Okay, I have drawn the graph in a different manner. No problem, no problem. The concept is fine. Concept is correct only. Don't get confused. Concept is perfectly correct. One change just I'll do for make this graph correct. Otherwise, everything we have to change. I am just taking this as a general graph. Just consider not for with respect to this reaction that I've done. Just general graph you assume here. Everything is fine. Just remove that reaction from the mind. Just you see this, reaction. I'll just write down one random reaction just to understand this graph. Okay, I'll give you one general reaction also. Suppose we have a reaction A2 plus B2 gives 2AB. Okay, and in this we have A2 gives 2A. A2 gives 2A. The first step, and suppose this is the slowest step I am assuming. Okay, everything is correct. There's nothing wrong with the concept. Just 2 minutes to give me. Then this A reacts with B2. It forms B2A. Right. And then this B2A again reacts with A. It forms 2AB. This is the 3 step we have. And this is the fastest step. This is the fastest step. And overall reaction is A2 plus B2 gives 2AB. Now you consider with respect to this we have. Here initially we have A2 plus B2. Okay, A2 plus B2 should be the slowest step, that's fine. So it converts into 2A first, the intermediate, then it converts into B2A, another intermediate, and then it converts into 2AB, the final intermediate. All the concepts are same, nothing is different. Just I should have taken this activation energy should be the least. This should be the maximum. By mistake, I've drawn this, no problem. Concept you can understand. Okay, so what I said, as activation energy decreases, K increases. K increases means rate of the reaction increases. So based on this activation energy that you have here for the 3 step, which one is the slowest step? If I tell you this is step 1 from here to here, step 1. From this point to this point, it is step 2. And from this point to this point, it is step 3. Tell me, step 1, step 2, step 3. Based on this information, which one is the slowest step? The one which has the highest activation energy. Isn't it correct? Right. So what you can do, the slowest step, if they ask you in the question by giving you this graph, if they ask you, which one is the slowest step? The one which has the highest activation energy, highest EA, which is for this example, we have a step 1. No doubt in this? Correct? Tell me.
So, sir, dissociation of iodine is the slowest step in the previous case.
No. That's what I said. This, see, just 1 second. This reaction is correct. Okay. This one is correct. You just leave it here only. It is done here. Finish. Okay, sir. Now you focus on this. That's what ideally I was trying to draw the graph for H2I2 reaction. But by mistake, what I did, I took this activation energy as the maximum. I should have taken this the minimum. Right. This should be the maximum. But since I have done this graph, so for this I have written this reaction. Now you consider this graph for this reaction. Fine. H2I2, let it be. If you want, I can draw the graph of that also after this. Okay. A2 gives 2A. Suppose it is the slowest step. Reacts with B2. Fast. Overall reaction is this. So first step is what? A2, B2 converts into 2A. Then 2A converts into B2A. And then this B2 converts into AB. So this graph I have drawn for this reaction. Now you suppose if this graph is given, reaction is not given, graph is given, and they'll ask you which one is the slowest step. What you will do? You'll just see which step has the maximum activation energy. Because we know as activation energy decreases, K increases, reaction becomes faster, correct? Because the reactant molecule has to overcome only this much of barrier. It can easily overcome this. But if it has to travel a lot of this difference in energy by collision, it has to reach first this point and then come to this point, correct? So this is obviously difficult to reach at this point. That's why the step is the slowest step we have. That is what theoretically you can understand from this graph. But mathematical relation we have here. As activation energy decreases, K increases, rate of the reaction increases. So if they ask you which one is the slowest step is the one which has the highest activation energy, that is the step 1 for this reaction. Now, if I ask you which one is the fastest step is the one which has minimum activation energy. And that would be what? That would be anything between the two. For this graph, if I draw, in this two, this looks like the minimum. Okay, that's why step 3 with respect to this graph equation, step 3 is the fastest step we have. If they ask you the number of steps in this, in this reaction. So with the graph, the number of steps is nothing but the number of peak we have. 1, 2, 3 steps, number of peaks. Number of intermediates are 2. That's the 2, 3 points. Any doubt you have till here? One more property we need to discuss here. Any doubt in this? Tell me.
No.
Clear? Yes.
Yes, sir.
Now, could you tell me the first step is indo or exo? The first step is indo or exo. Since the energy of reactant here and here, the product that you get in the first step, which is an intermediate actually, but the energy of intermediate is more than to that of the reactant. Hence, the first step 1 is endothermic. With this graph, we can say. The second step, you see the energy of the product of the second step is lesser than that of the reactant. So it is exothermic. Okay. Third step is also exothermic. Right, exothermic. Overall, the behavior, if they ask you endothermic or exothermic, overall the reactant energy is this, product energy is this. Then if you look at the difference over here between the reactant and product, then we can say this much of energy delta H it will release in the reaction, and overall the reaction is exothermic in nature. Tell me, any doubt in this? So 3, 4 informations you should know from this graph. Number of steps, that is the number of peaks that is given. Which one is slowest step, which one is fastest step, that you can understand by looking at the activation energy of the graph. The behavior towards the heat, if the product energy is lesser than to that of the reactant energy, overall the reaction is exothermic. Each step we can define or we can understand on the same logic. Okay, energy of this is more than this, endothermic, less than exothermic, less than exothermic. Clear? No doubt? You want me to draw the graph of H2 I2 also? H2 I2 you want me to draw? H2 I2 I'll draw that. Okay, graph of H2 I2. So I'm assuming what you see, I'll go back and see, because we don't have exact data for this. We know the overall, the energy, overall this reaction is exothermic, basically. Overall it is exothermic. I know this, I'm telling you this information, correct? Exothermic. These two are fast step, but we do not know exactly which one is the fastest one. That we cannot say. So these two activation energy we cannot compare. Okay, and for this one we can say slowest it is, so its activation energy is maximum. Okay, so let's not focus on the activation energy EA1 and EA2. Right, we don't have idea of this two. Overall idea we have the reaction is exothermic, and activation energy EA3 is the maximum we have here. Yes, so with this information I'll draw the graph of H2I2. You see this. So we have a same coordinate X and Y. Okay, so I'm assuming that the energy of reactant is, suppose here, somewhere here we have energy. Reactant is this, and this is the energy of the reactant. So first step is what is the fastest step, correct? Sorry, fastest step we have. So suppose it goes like this, and then again it goes like this, and then the third step is this. Overall it's come down, because I know that the graph reaction is exothermic, so product ka energy should be lesser than the energy of the reactant. This is the activation energy of the first step EA1. This is EA2, and this is we have EA3. So we start with H2I2. This is the first intermediate 2I. This is H2I, and this is 2HI. Third step you see has the maximum activation energy. So this is the slowest step we have. With this graph, it is the slowest step. This too, depending upon activation energy, we can say, okay, this is the nature of the graph we have for H2 and H2. So basically what they do, they'll give you the graph like this, okay? And they can ask you any questions like the 3-4 information that I've given you regarding endothermic, exothermic, slowest step, fastest step, okay? Number of intermediates, number of peaks, number of steps that you have. Based on these 3-4 information, they can ask you any question based on the graph, right? So you should know that from the graph, what all things we can conclude. This graph is for H2 plus I2 gives 2HI. Any doubt in this? All of you understood? Please respond quickly.
Yes, sir.
Fine. Fine. So we'll take a break now. After the break, we'll two more topics we need to discuss. A big topic. Okay, both are. The last one is quite big. The second last one is not that big. Okay, so after the break, we'll start with the collision theory of reaction, and then we'll see some miscellaneous reaction and how to derive the expression into that. So take a break. We'll start after the break. 7:05 we'll start. Take a break, guys.